Hey everyone, back again. This is the lecture for Chapter 4, which is Earth Structure and Plate Tectonics. This is over Lesson 2. Um, Again, I mentioned in my intro video and put a note in our materials as well. Um, we have a lot of information and material to cover for this bi-term, and because we did it as a bi-term, I have to double up some of these lessons. So this one and the next one, this lesson and the next, we're going to have 2 chapters per lesson, just because I had to work it in like that to be able to cover everything. After that, it should be just 1 chapter per lesson, so that will even out a little bit. And I decided I had to do that. I decided to do it at the first of the semester instead of the end of the semester, because I know a lot of people have projects due and things like that at the end of the semester. So I just thought the material would be a little a little simpler at the beginning of the semester. Plus, maybe your workload was a little bit less. So I wanted to do that here at the beginning. So this this lecture video is going to be a little shorter than the first one. Couple reasons. One is there's not as much material in this particular PowerPoint, and because this is not my area of expertise or something that I want to cover in great detail for the purposes of this course. Keep in mind, we talked about in the introductory chapter about the scientific method and people's specialties and how we study these things. Just keep in mind that any one of these chapters that we're talking about, we could teach an entire course, entire semester on that one topic. That's how in-depth these things are. So what we're learning, especially here at the beginning of the semester, is just a quick 50,000-foot view of the information that we need to be able to move forward throughout the semester. So, Earth structure and plate tectonics. Again, the first thing that we're going to talk about is the deformation of rocks. So there's a reason that we're going to talk about this. So more or less, when we get into plate tectonics and the processes that govern the surface and the inner workings of the Earth, especially for us here on the surface, is the movement of plates, the movement of rock layers. And we have to understand how those respond to one another when they're put under great forces of nature. So as we go through this lesson, we're going to be talking about, first of all, we mentioned it in the last lecture about the sections of Earth, the inner Earth up to the crust. And then we're going to talk about how that crust moves around and the stresses that we put on those different plate boundaries, which are made up of what we've been talking about, of rock. So this is a simple little visual aid to let you know what these different forces are that act on rock at these plate boundaries. So you see the far left's an original. That's just a little grid that they have, and that's just showing you, okay, this is the normal. This is how it is when there's no stress on that rock. Compressional means that it's pushing together. So if you take something and squeeze it together, think of a loaf of bread. If you took it at each end and just crammed it together, you could smash it together. And that bread, while it's not going to be pretty and sliced and neat like it was before, like you like to eat it, it's still bread, but it's compressed. And it's taken up a little less area, but it's a lot more dense. So keep that in mind when we're talking about rock layer. Tension is the opposite. Tension is stretching outward from the center. So think about grabbing something and pulling it completely apart. That's what tension is. And then shear, it has the lines kind of at each corner. Shear can mean a couple of things. One thing is it's kind of twisting, maybe, is a good term for it. It's kind of got forces on, in this case, each corner, on, or maybe diagonally sometimes. And shear means it's kind of rubbing past each other or twisting. That's what shear means. We always would put our hands together and move one hand up and the other back. That's shear, moving back and forth, that boundary. So when we talk about the deformation of rocks, there's a lot of things to consider. First of all, what type of stress is being put on those rocks? Other things include the chemical makeup of those rocks, the density of those rocks, the brittleness of those rocks, the elasticity of those minerals in those rocks, the heat, how hot are these rocks? As you well know, if you take certain materials and you heat them up, think about plastic. In a normal temperature, plastic is plastic. It's kind of hard. It depends on how thick it is, but it's a solid. Can't really break it that easily. But when you heat it up a lot, it melts. If you heat it up a little, it doesn't melt all the way, but you can kind of deform it and shape it and move it. And you think about rocks like plastic almost. That's how they react to these different pressures. Now, of course, rocks are much different, and even rock to rock is different depending on its makeup and depending on its pressure and its temperature, how deep it is in the earth. Is it close to that magma down there where it can be more bendable, maybe, under pressure, under heat? Or is it at the surface? It's really brittle, so when it does have these forces on it, it's going to crack, it's going to break, it's going to snap. Those are the things that we have to keep in mind when we're thinking about how these actions are going to affect the rock layers. The idea of seismic waves. So seismic waves, you can send seismic waves. We probably all know seismic waves when we talk about earthquakes. The seismic scale, it was a 5.0 or a 6.0. That's how we measure seismic waves. But basically a seismic wave is a wave that travels through the earth. And that can be natural, like from a breaking rock from an earthquake, or we can make those seismic waves. And we can test what's underground. That's a very common thing in engineering and construction. If they want to know what's underground, they can set off charges on the surface. Think about a little mini stick of dynamite, just a little bang grenade almost. And you stick it in the ground and you pop it. And it sends sound waves through the ground. And by the way those sound waves bounce around down there, they put sensors up all around that. And as long as they know where that point is coming from, the way those waves reach those sensors can tell them what the density of the earth is under there, if there's any changes in density, how deep those changes are. And that's the same way that we measure earthquakes, because we have sensors set up all over the world. So whenever there's an earthquake, say in South America, we can triangulate on that point from all these sensors around the world and measure the difference in those seismic waves, and we can tell what strength it was, where it originated, etc. And that's because those waves reflect and refract when the density of the earth and material changes. So again, we mentioned this in the first chapter, the last chapter that we had a lecture on. The crust is called the lithosphere. It is approximately 15 kilometers deep, give and take. Depends on where you're at and what's on top of it. If you're on the bottom of the ocean, it might be a little thinner. Up in the mountains, it's going to be thicker. The mantle, you can see here, I don't have to read each one of these to you. The outer core, remember there's actually two cores, the outer and inner. The inner core is a metallic solid. It has a lot of nickel, a lot of iron in it. And the outer core is a metallic liquid. It's molten. So it's actually in motion. It's moving and circulating. And that movement is very important. That molten core around the inner core is very important to how our Earth functions and even why we can live here. It provides us with a mechanism that we have life here on Earth. It offers us several protections. Our biosphere, our hydrosphere, all these are driven by what's going on in there. Even though it seems like it's out of sight, out of mind, we never think about it. It's essential to what's going on this planet right now. So again, that inner core is solid. It does rotate. That's what causes the Earth to rotate. And it rotates faster than the liquid outer core. The liquid molten outer core rotates just a little bit slower. And what that does is those metallic materials in that core generate a magnetic field. That is crucial to life on Earth, because even though we don't see it or we don't feel it as living organisms, that magnetic field puts up a shield in space. That magnetism deflects harmful solar rays from hitting the Earth directly. It deflects them around the Earth. And that allows us to be able to have a habitable environment here on Earth that we and all the other animals in our biosphere can live in. And that's crucial. So the internal heat of Earth, in one of the videos I share with you in your lesson, it really explains this really well. You know, this all started back when the solar system was born and the planets were formed. There was a lot of frictional heat from impacts from different celestial bodies. We also have a lot of radioactive heat with the decay of uranium, thorium, and potassium in the core. And again, we have that molten outer core that keeps moving, and that friction and that pressure that it creates also generates heat. So it's kind of like a self-sustaining oven, even though it is, over time, slowly losing heat. We're talking about on the order of hundreds of millions or billions of years. So nothing that we're going to have to directly think about in our lifetimes. But at some point in the way, way, way distant future, this thing's going to cool and things are going to change. So again, we talk about convection at the bottom, that heat in the outer core. Convection, it's driven, the heat. Think about a pot of boiling water. You put the heat on the bottom, it gets hot on the bottom, and then it boils to the top, and it recirculates around the sides. That's what convection is. The heat rises, so it creates a loop. So it continually kind of think about it boiling under there. That's what convection is. Early in geologic science, I guess, they mentioned Taylor here, but Wagner actually introduced the continental drift theory. Taylor first suggested that they were joined just by looking at maps, more or less, and Wagner took it to another level with more studies and developed that we had a supercontinent called Pangaea, that they were actually all together at one time, and they had drifted apart over geologic time. One way that we can determine that, and they started studying that back in those days, was, first of all, like I said, you can kind of piece the continents together as the maps down here, down below, the globes show. In addition, if you look at rock layers from this time period, we can find some common fossils and organisms that occur throughout this, what would have been a supercontinent, that without those continents being somewhat together would have never evolved the same as they were found in the fossil record. So that's another indication that yes, indeed, these continents at one time were together. So another thing that really are several ideas that really kind of push this evolving theory back in those days of plate tectonics was we were able to have technology to start mapping the ocean floor. We can look at what are called ridges under the ocean floor. These are divergent plate boundaries. They're actually moving apart. So you're creating new rock layers there all the time because the magma is bubbling up to the surface, becoming lava under the sea, solidifying, cooling, and solidifying. And we can study those different rock layers as they were formed historically. That also is the way we study the magnetic pole reversals. They reference this in your textbook. I'm not going to get into a lot of detail on it, but basically in these linear deposits along these these ocean floor trenches, any magnetic minerals that formed, they indicate the magnetic north or south at that time. So we can go down there and study these linear features and see that the magnetic poles have swapped, reversed over time at different parts of our geologic past. We are also now able to map the location and depth of earthquakes and the polar wandering. That's kind of like the true north. What I referenced before is the magnetic poles reversed. In addition, the planets wobbled just a little bit over time, over geologic history. So the true north and south poles have wandered a bit over time as well, and we can also decipher that from that geologic record. This is just showing some of the trenches in white. You see all these trenches on the ocean floor. These are primarily divergent plate boundaries. And if you're wondering or haven't read your lesson yet, plates occur with both land, continents over the top of them, and with the seafloor over the top of them as well. For instance, the Pacific plate is almost entirely under the ocean, whereas the North American plate's got a huge continent on top of it, as does the South American plate. So these are the divergent trenches that we can study. And again, this goes back to the magnetic reversals I was telling you about a couple of slides ago. As these trenches separate, they create new rock layers in a linear fashion. And we can look at the metallic elements in each one of these, and we can see over time that the poles did indeed reverse. The magnetic poles did indeed reverse. Here's a map of earthquake locations. Since we started recording these things, I don't know exactly how many years it is, probably the last 70 or 80 years or so, I would assume. And there's no coincidence here that this is not random. If you look at a map of the plate boundaries that separate the 17 plates in our lithosphere, you will see that these earthquakes pretty much happen along those plate boundaries. And you have a couple of diagrams here. The lithosphere is going to be your very top layer, the crust, and just a little bit of the mantle is included in the lithosphere. And then the asthenosphere is predominantly the mantle. You have magma pockets that bubble up at plate boundaries at times or near plate boundaries, and you have earthquakes that happen. But just be clear, we're going to go over this in the following chapters, that earthquakes and volcanoes, although they both happen in similar environments with regards to plate boundaries, they're not always just together. You have some plate boundaries that will produce earthquakes and don't have any volcanoes, and vice versa, and sometimes they have both. So we'll talk about that more in detail coming up, though. Again, these are some diagrams from the textbook. I'm not going to spend a lot of time on that. I'll keep referring to plates. These are rigid slabs in the lithosphere. So basically, this is one solid kind of piece of that crust that's floating on top of that molten inner core, actually on the mantle, but all that's floating on that molten inner core. The plate boundaries are moving past or into one another, or diverging away from each other. That goes back to our tensions that we saw on that flush side, the one that when you compress or transform fault, they shear apart from each other. They may override each other, a convergent fault. So here are the plates. Different colors are different plates. You can see here is North America. There's the continent. We also have some of the Pacific Ocean that lies on the North American plate. The Pacific plate is here. Nazca plate is out here in the Pacific as well, but it's separate from the actual Pacific plate. You have the South American plate. So there's plates all over the world. You see there's one pretty much that covers India by itself. We're going to mention that in just a few minutes. And here are your types of plate boundaries. So going back, where these plates come together, all these black lines, you're going to have one of these things happening that you see at the top. Either a divergent boundary, which means it's tearing apart. That's going to be mostly your trenches, your plates that are ocean. So deep in the ocean, you're going to have these right here. We do actually have one that's in Africa, in this area up here, that's actually starting to tear the continent of Africa apart just a little bit. You're going to have your convergent boundaries, which are smashing into each other. So you have a couple of different types of those. One's called a subduction. We'll go over those a little bit more in just a second. This one right here you're seeing is called the subduction fault, and what that means is this plate right here is actually hitting this one. You see a little bit of mountain formation and volcanoes here, but the crust itself is actually going down under this one. And you see volcanoes form actually quite a ways from that actual boundary where we have a trench here. So we're going to go over that more in just a second as well. This is just showing the convection underneath in the mantle. That heating is allowing this asthenosphere. The mantle is not as solid as the crust, therefore you have some elasticity, so these plates move around up here and on top of the asthenosphere, and that's where you get your plate boundaries when these plates, they start either crashing in, moving apart, or shearing across, up and down one another. This is just a visual effect for how this is gravity and snow, but it's showing how materials can slide on top of another material if it has the right conditions. In this case, it's gravity pushing this snow down the front of this car. Again, divergent faults at plate boundaries. They're ocean ridges. It's actually the fault itself usually has a valley in it, but ridges build up around it where the rock is actually forming. A rift valley is what happens if it happens on land, like on a continent. Those are a little bit more rare, but they do happen. Like I said, there's one in Africa that's pretty predominant. Convergent, you have the hitting each other, just ramming into each other. Ocean to ocean, if you have convergent on the ocean floor, you typically see islands form there, like the Hawaiian Islands or volcanic islands that are not too far from a plate boundary. Ocean continental arc, that is a boundary. It's a subduction boundary, like I said before. That's where the plate, typically the ocean plate, is going to go under the continental plate. Typically there, you're going to have mountains. Sometimes you'll have volcanoes, sometimes not, but you'll also have a trench that's under the ocean, on the ocean floor, a deep trench very near the edge of the continent. And then you have continent to continent convergence zones. And that's when, in the case of what I just showed you earlier, the Indian subcontinent actually slammed into the Asian continent and produced the Himalaya mountains. So that's an example of that. Transform at the bottom, that's the last one. That is actually sliding beside one another, and that's what the San Andreas Fault is in California. So again, we have divergent plate boundaries. They're moving apart, typically found on the ocean floor. But you can see here, there's one in Africa. There's also one that goes along the bottom of the Red Sea. It's kind of a continuation of that one in Africa. This is the Great Rift Valley in Africa. It's very predominant. If you ever see air photos of that, I think there's a picture later in this slideshow. Here you can see the Red Sea. That's where one is. It's pulling these land masses apart. Here is a convergent plate boundary. This is South America. This is the Nazca plate. This is a South American plate. You can see the deep blue right here. That's the trench that's just offshore, where that boundary, that plate is actually going under the South American plate. And you see the mountain range, the very high mountain range here on the coast of South America. That's actively still being formed by this convergence. There are isolated volcanoes, not too many active volcanoes down there, but you do have them every now and then. My wife is actually from Lima, Peru, which is going to be right here, so I spend a lot of time in Peru. And it is very, very common to be driving down the road and see everybody standing out in the streets. And at first I thought, why was everybody standing in the streets? And the reason is because they have earthquakes so often that they evacuate buildings every time that there is a moderate earthquake, which would be a decent earthquake here, but to them it's just moderate because they have them constantly. So that's a very common occurrence down there. Again, this is the one I just mentioned, the Indian, they call it the Indian subcontinent. It's now all part of Asia, but before the continents came together, it was its own continent. It slammed into Asia and created the Himalaya Mountains here. And here we have a transform boundary. And if you see here, the transform boundary is going to be along here. So right here, you can see the arrows going apart. Those are rift valleys. Those are pulling apart. But along the edge of these plates are moving side to side. This one left, this one right. So you have a shear effect. And when you have a shear effect, what you have is, like in California, the San Andreas Fault, is those plates will kind of get stuck together for a little while. And you know how you got something stuck and you rip it apart and you pull and pull and pull and all of a sudden it snaps apart? That's what happens on those plate boundaries. They're up against each other, they kind of get stuck on each other, and eventually they give. And when they give, that creates a huge earthquake. And that's what you see in California. You can see here how that is moving. That jagged line right there is representing that transform fault. But you see, once you get up here into Northern California, or up here into Northern California, you see the San Andreas Fault right here. All of a sudden, it turns into a convergent fault up here in the northern part of the plate, and you get the Cascade Ranges up here. So up here, you might see Mount St. Helens, a volcano, erupt. In California, you get a lot more earthquakes. So plate boundaries and people, of course, we have natural hazards. We're going to talk about those in more detail in the next lesson. So I'm not going to go into them a whole lot right now. But the natural resources, whenever you have mountain building and tectonic activity, you have a lot of mineral resources that are coming up and being deposited in these mountains. So a lot of mining activity typically happen in these areas. Climate. The upheaval of the mountains can actually affect climate in a continental way at times, like the Andes, the Rocky Mountains in the United States, the coastal mountains out in California. They all have effect on climate, and we'll talk about that a little bit later as well. One more thing to touch on, we have the ocean currents. Because these plates do move, and because of the mountains that they form and all the processes that come together, we have ocean currents that flow under the sea. These ocean currents are critical in life on this planet and the distribution of our climate in warm and cold temperatures. And again, we'll talk about this a little bit more later, but this is very crucial to the biosphere that we're going to talk about later. This is just a slide. You can read about this in your textbook. There's a deep ocean trench here. This is in Southeast Asia area right here. You have the Philippine Sea, the Pacific Ocean, the Indian Ocean out here. There's a deep trench right here. And there's a definite difference in life and evolution on this side of this trench versus this side of this trench. That just shows what can happen when you have something geologic happening in something like the biosphere. So that's pretty much it for this lesson. I want to get off there as quick as possible. Again, if you have anything you need from me, please let me know. I'm always happy to help. And if there's something going on, like trouble with homework or the online system, I don't necessarily know about it unless one of you lets me know about it. So please reach out if you need anything. Thank you.